In this screencast, we're going to talk about what happens when velocity changes. We'll discuss instantaneous position, velocity, and acceleration, and then we'll also talk about the ideas of average velocity, average speed, and average acceleration. So let's first start with a demo where I show you a cart that has not a constant speed like we looked at last time, but a changing speed. This is a fan unit, or a fan cart. It's got this remote control fan that I can turn on and off. It's remote control in the sense that it comes from a remote control airplane. And it's attached to this cart that can move with almost no friction along this track. So this won't stay at the same speed. It'll speed up and up when I place it on the track. So let's see what the motion detector says about its motion. Here's what the motion detector and the program Logger Pro report about the position and velocity of that fan cart. You can see from the velocity as a function of time graph that the velocity is changing. This region that I'm highlighting here is what I would call the relevant region. It's the time when the detector was detecting the fan traveling away from it. Before that, the fan was just resting in place, and after that, I'd taken the cart off the track so the detector wasn't detecting anything. But during this relevant region, you can see that the velocity is increasing, and it seems to be increasing roughly linearly. Before, with constant velocity, with the blue and red buggies, we saw that the position increased linearly as a function of time, but that's not the case here. This looks like a parabola, and indeed it is the shape of a parabola. And so I can't talk about the slope of the position as a function of time graph like I did before, because there is no one slope that describes this curve. However, let me show you what I can do. I can use this tool called the tangent tool and see what Logger Pro is doing. See that black line here? What it's doing is, for a particular time instant, it's drawing a line that is tangent to the curve at that point. You can sort of imagine doing this by hand. You could just go to this location on the graph and draw one straight line tangent to the curve at that point. And then, now that you've drawn that straight line that's tangent, you can say, what is the slope of the line that I have drawn, the slope of the tangent line to the curve? And Logger Pro is reporting that. For example, at this particular instant, which is about 2.1 seconds into the recording, the instantaneous slope of the tangent line is about 1.05 meters per second. Meters per second, does that make sense as the slope of the tangent line? Well, I think so, because the tangent line would have a rise, an amount of meters, and a run, an amount of seconds. Okay, well, this meters per second as the unit of slope of the tangent line is suggestive. We had found before that the slope of position with constant velocity was equal to the value of velocity. Now, watch what happens when I use the examine tool on the velocity graph at the same time as I use the tangent tool on the position graph. The slope of the tangent line at this instant is 0.407 meters per second, and that is also the value of the velocity, the instantaneous value that the velocity has at that instant. Here, there is a steeper slope of the tangent line in the position graph, and there's also a higher value of velocity, and those features are the same. It looks like the slope of the line tangent to the curvy position function is the instantaneous value of the velocity. And the slope of the tangent line is a little cumbersome to say all those words each time, so I will just use the word derivative. The derivative of the position function is the instantaneous velocity at that time. You can still talk about, let me get rid of these, you can still talk about the integral of the changing velocity as a function of time function over a time interval between this time instant and that time instant. This red shaded region has a value of 0.7, let's see, seconds times meters per second is a meter. And again, that is the value of the change in position, the value of the displacement. Here, the position at this first moment is 0.3 meters. I can see that from this reading down there. 0.34, and then it changes to 1.07, which is about a displacement of 72 centimeters. So we found, as with constant velocity, that the derivative of position is velocity, and now we take that derivative to mean the slope of the tangent line. And we found again that the integral of velocity is the change in position, the displacement over a time interval. Let's keep rolling with Logger Pro's analysis of the fan cart's motion. Here at the bottom, I have added the acceleration as a function of time graph, and now let's talk about what acceleration is. Again, this is the relevant region, the time during which the motion detector was actually detecting the path of the cart, as opposed to just a motionless cart, or this is the time before I had taken the cart off of the track. This is the relevant region. During this time, we have a velocity that appears to be increasing roughly linearly, and I'll suggest that we have an acceleration that looks roughly constant. There are some bumps along the way, but overall it's more or less constant. And what I'm going to do here is I'm going to find the slope of the velocity graph. And let's see, what should the units of the slope of velocity graph be? Well, it should be a rise in meters per second over a run in seconds. So that's meters per second divided by seconds, which mathematically works out to meters per second squared, which is the unit that Logger Pro is actually reporting the acceleration in. And check it out, if I look at the, oh, I did this wrong. To do a linear fit to the velocity, not find the statistics on it. Boop. There we go. The slope of the velocity line during this interval is roughly 0.77 meters per second per second, 0.77 meters per second squared. Meanwhile, the average value of this acceleration is about 0.78 meters per second squared. So, as with constant velocity, where velocity was the derivative of position, the slope of the position as a function of time graph, which was linear, here I think we have discovered that acceleration is the derivative of velocity. It's the time rate of change of velocity. Very good. Well, I wonder then if acceleration is to velocity as velocity is to position, perhaps we'll have something meaningful to say about the integral of acceleration over a time period. Logger Pro just reported that during this time period, and I will attempt to roughly select the same time period here in the velocity graph, the integral of acceleration is 0.57 seconds times meters per second squared, because it's like a rectangle whose height is measured in meters per second squared and whose base is measured in seconds. And so a second times a meter per second squared is a meter per second. And let's find out if the change in velocity is roughly the same as the integral of acceleration. So let's see, we start off this interval at a velocity of roughly 0.25 meters per second. Then at the end, it's roughly 0.84. And I will say that, yes, that is roughly a change in velocity of 0.57 meters per second. This time, I'm going to let the fan cart speed up towards the motion detector. Here we go. Can you predict what that graph is going to look like, what the position, velocity, and acceleration graphs will look like? Why don't you pause the video and see if you can make a prediction about what they'll look like. Here's what they actually look like. There's some mess here involving the time that I set the cart onto the track, but I would say the relevant region here is this region, when you have a roughly linearly decreasing velocity, a velocity that is getting more and more negative, a velocity that is getting faster and faster towards the motion detector, and you have a constant negative acceleration. And that acceleration has roughly the same negative value, about minus 0.75 meters per second squared, as it did when the fan cart was moving away from the detector. Now I'm going to show you one more different type of motion, and why don't you pause the video then, after I show you that, so that you can see if you can predict what the position and velocity and acceleration graphs will look like before I reveal them on Logger Pro. This time I'm going to have the fan going that way, and I'm going to give the cart an initial push towards the motion detector, and let's see what Logger Pro has to say about the motion. So here's what Logger Pro had to say about that motion, and I'm sorry that the line color is a little light. I was having trouble figuring out how to change that. However, let's look. We have a fairly linear velocity as a function of time, and we have a parabolic looking position as a function of time. And during the relevant region, I guess the time between when I gave the cart the push and the time when it came back to me and I caught it, we had roughly constant acceleration as well. This is maybe surprising to see that the acceleration doesn't change, because after all, the motion of the cart seemed to change a fair amount. And now we see that motion is kind of a fuzzy word. It doesn't clearly refer to position or velocity or acceleration. It's just sort of a word that blurs all of those together. And I would say that even though there was a change of direction, the acceleration was constant. And that makes sense because the derivative of velocity is constant. The slope of the tangent line, the tangent line is the line itself with velocity because it's a linear function. If you look here, you have you have a point where the position function has a negative slope of the tangent line, but then down here the tangent line is horizontal, has a slope of 0, and then here you have a point where the tangent line to the position function is positive. And so it's still the case that at every instant the velocity is the derivative of position and the acceleration is the derivative of velocity. And you can see that that motion with the fan cart was a motion that involved constant acceleration. So let's codify and talk about what we learned from that set of demos. When velocity changes, the derivative of the position function is the instantaneous rate of change of the position function, and that is the same as the slope of the tangent line that you can draw to the position function, and that is the same value as the value of velocity. The value of velocity is the derivative of position. The value of velocity is the slope of the tangent line to the position as a function of time curve. Okay, and as we had talked about with constant velocity, it's still the case that even with non-constant velocity, the integral of the velocity function over a time interval is the change in position, the displacement of an object. Meanwhile, and similarly, the derivative of velocity is acceleration. For example, could you solve this problem? What is the value of the acceleration indicated in that graph? You might pause the video and see if you can figure it out. Well, the derivative of this velocity function, because it is a linear function, is the same as the slope of the velocity function. So we can just take the rise over run, and the rise there is, let's see, between 2 seconds and 6 seconds, there has been a decrease in velocity by 8 meters per second. So the change in velocity is minus 8 meters per second, and that divided by 4 seconds is minus 2 meters per second per second. So the units of acceleration are meters per second squared. And what that just means is that for each second, there is a decrease in velocity of 2 meters per second. That's what an acceleration of minus 2 meters per second squared means. All right, it is also true that the integral of the acceleration function over a time interval is the same as the change in velocity. It's not that the integral of acceleration gives you the value of a velocity at a particular time moment, but it tells you the amount that the velocity has changed. For example, if this acceleration as a function of time graph describes the motion of an object, can you tell me how much the velocity of this object has changed between 1 second and 5 seconds? You might pause the video and see if you can answer that. Well, the way you can find the change in velocity is to find the integral of acceleration, and that's like the area of that rectangle. I expect that it's going to have a negative value because this rectangle is below the horizontal axis. And let's see, the base of this rectangle is 4 seconds, and the height of this rectangle, if you like, is minus 3 meters per second squared. So 4 seconds times minus 3 meters per second squared is minus 12 meters per second. That's not the value of the object's velocity at a particular instant necessarily. That is the amount that the velocity changes between t equals 1 second and t equals 5 seconds. So we've now introduced a new model. Last time we talked about the model of constant velocity, and here we are talking about the model of constant acceleration. The fan unit is something that moves with roughly constant acceleration. Maybe not perfectly, but approximately constant acceleration. We will have multiple things to say about this model of constant acceleration. We'll have verbal ways of representing it, we'll have mathematical ways of representing it. We'll talk about those next time. But for right now, we have talked about the graphical representations of constant acceleration. They include a constant acceleration as a function of time, a linear velocity as a function of time, and a quadratic or parabolic position as a function of time. By the way, exponential refers to the function 2 to the x, not the function x to the 2. And so I would not say this is an exponential function. I would say it's a quadratic or parabolic function. And we will talk about the math relationships between these variables during some time in the future. But for right now, let's see if we can do this. Can we complete the missing graphs? If we're given this position as a function of time graph, can you draw the velocity as a function of time graph for this object and the acceleration as a function of time graph for this object? By the way, what I'm asking for here is a sketch, not a quantitatively correct graph. And so I don't actually need to label the units. I don't need to say x is measured in meters, because whether x is measured in meters or miles or inches or millimeters or feet, this will always be the shape of x as a function of t. And the velocity as a function of time will always have the same shape. And the acceleration as a function of time will always have the same shape regardless of their units. As soon as I drop a number onto this, it becomes a graph. Like if I say, oh yeah, there's 1, I need to say 1 what? Is it 1 millimeter or is it 1 mile? If I drop the 1 here, is that 1 meter per second or is it 1 mile per millisecond? But for right now, we're talking about sketches. And so this is a fairly common exercise in calculus classes and in the unit that we're talking about now, which is called kinematics in physics, the study of motion, motion. And I will try and draw the velocity as a function of time graph, but I won't try and do it all at once. I'll take it piece by piece, because especially if this is a new challenge for you, you might feel overwhelmed by just the task of drawing the whole velocity as a function of time graph. You don't need to do that. Let's just look at the initial moment. At the initial at the initial moment, if you imagine what the slope of the tangent line would look like to the position as a function of time graph, you'd see that it would be a large negative slope of the tangent line, which means we have a fairly large negative velocity. I will draw right there as a dot. At this moment, look, there would be a horizontal tangent line, so the value of the velocity there is 0. The slope of the tangent line would be 0. And here, you would have a pretty large positive slope of the tangent line. And I know that if this is a parabola, then this should be a linear graph. And indeed, at all of the moments between the initial moment and the moment where there's 0 velocity, the velocity is always negative. There's always a negative slope of the position function, but it's getting less and less negative. And then after that moment, there's a positive slope, and it's getting more and more positive. So I took this piece by piece and drew the velocity as a function of time graph. Now, the acceleration as a function of time graph. Well, acceleration is the derivative of velocity. It's the slope of the velocity as a function of time line. And this velocity as a function of time line has is constant and positive, so there is a constant positive acceleration. Done. Let's do a different example that might be a little more challenging, or maybe not. Before I do that, actually, let me just note explicitly, there's a very strong tendency by human beings to look at a graph doing this problem and copy the same graph. That is to say, if I were drawing this velocity as a function of time, there's a strong tendency to say, oh yeah, it starts off positive and then gets lower and then it goes to 0 and then it gets bigger again. So like that, or maybe I want the velocity to be linear because I know that there should be linear velocity with a parabolic position as a function of time. But see how I've sort of polluted my reasoning there by just trying to copy what that looks like? That is a tendency that you might encounter, and it's reasonable because we're very visual creatures, but don't do it. Good. Okay, so here we're given a constant negative acceleration as a function of time, and we're asked to generate the velocity and the position graphs, and I guess the initial value of the velocity has been specified. Sometimes a problem will ask you to sketch velocity and position without specifying the initial value of velocity, and you just need to make an assumption, and any assumption will be fine. So let's look. Constant negative acceleration, constant negative slope of velocity. Nothing changes there. Now, what will the position as a function of time look like? I'll try and take it bit by bit, not all at once. I know it's going to look like a parabola, and is it going to be an upside down? Which way is it going to open? I know that the parabola will have a vertex at this time instant, if I'm imagining stacking them vertically, because here there's a 0 value of velocity, a horizontal tangent line to the position. We start off with a large positive velocity. And so I think I'll try and draw this like that. There's a large positive velocity, and I'm going to draw the vertex there. And it's okay to take a couple of attempts. A large positive velocity, not an infinite initial velocity, but a large positive velocity. And then the velocity becomes negative and more negative. Okay, cool. Great. When is delta x negative? When is displacement negative? When is velocity negative? Let's see if we can generate an answer to those questions that is always true. Here's an example of a graph that would indicate a position where between the start and the end delta x is negative, and I think you can see that because there's a negative slope there, the velocity is negative. So maybe I'll say when an object is moving towards the origin, then it has negative velocity and its displacement will be negative. But check it out. Here, if an object starts at a positive or negative position and then goes into more negative territory, Well, is this object getting closer to the origin? No, this object is getting farther from the origin of position. So I guess it would be tempting to say when an object is moving in the negative direction, then it will have a negative velocity. It will have a negative displacement. But here's an object that spends sometimes moving in the negative direction, sometimes staying still, sometimes moving in the positive direction. Yet I think it's pretty clear that this object has negative displacement because it starts with a displacement of 0 from the origin. It starts at a position of 0 and then moves to a negative position, so it has to have a negative displacement. So here's what we can say that I think is true all the time. A displacement is negative when the final position is more negative than the initial position. And at a particular instant, the velocity is negative if the object is moving in the negative direction at that instant. Well, when is acceleration negative? Here's an example of an object that has constant negative acceleration. Looking at this first, looking at that first part of this graph, you might say, oh, this object has a velocity that's getting closer and closer to 0. It is slowing down. So maybe acceleration is negative when an object is slowing down. But check it out. During this next part, the object is moving in the negative direction. It has a negative velocity, but the velocity is getting more and more negative. So during this second time period, the acceleration is still negative, but the object is speeding up. It's not correct to say negative acceleration means slowing down. Here's what you can say. The acceleration is negative when speed is decreasing, moving to more and more negative numbers. That could either be slowing down with positive velocity or speeding up with negative velocity. If we were doing this live in the lab, instead of having you watch me talk on a screencast, we would act out a lot of examples. You might do that yourself. You might say, well, if I imagine having a track in front of me and that direction is positive, then let me see if I can act out this motion with my finger. Can you do it? Can you move your hand or your finger to act out this motion? That's a good way to test your understanding because it's expressing your mental model of constant acceleration in a different modality, the acting it out modality, the physical modality. I think that this graph would look like that. Sound effects, very necessary. When is acceleration positive? This is a situation where the acceleration is always positive. Either slowing down with negative velocity, right? Here there's negative velocity that's getting closer and closer to being still, closer and closer to 0 velocity, or speeding up with positive velocity. Those are both situations when there is positive acceleration. Is it possible to have velocity equals 0 at an instant where there's a non-zero acceleration? Why, yes, there is just such a moment. And this is what happened when I pushed the fan cart towards the motion detector, if you remember. The moment when it switched directions, it was instantaneously at rest, but it was accelerating the whole time, even though the value of the velocity was 0. The velocity was always changing in a way that it was getting more and more positive. So we did have 0 velocity at an instant where there was positive acceleration. All right. Let's imagine that this is the position as a function of time of an object. Can you tell me what the velocity of this object is? Why, no, it's a bad question, because there are different instantaneous velocities at different time instants. Here, the slope of the tangent line, the derivative of position, the value of the velocity would be positive but kind of low. Here, the slope of the tangent line would be positive and bigger. There are different values of velocity, so you couldn't answer the question, what is the velocity? But you could answer a slightly different question. You could answer the question, what is the average velocity of the object during this time interval? And you'd be answering this question. If instead of having a changing velocity, you were to only have one constant velocity, but you still covered the same distance, you still have the same displacement. What would that constant velocity be? That is the question of what is the average velocity. When you ask what the average of something is, you're asking what constant value would have given the same net effect as a given changing value. And in the case of velocity, the effect of velocity, if you like, is the displacement. You can see from this graph that the slope of that blue line, the average velocity, is the rise over run, delta x over delta t. So when velocity changes, the average velocity is equal to the displacement divided by the amount of elapsed time. Those angled brackets denote average. So in this case, I guess there's a displacement of 6 meters in 2 seconds, so an average velocity of 3 meters per second. That's how you can find the average velocity. Here's an analogy. If you have 3 tests and you get an 85, an 80, and a 90, what is your test average? Well, more than the answer, I want to focus on what that question means. What the question means is what constant rate of points per test would have given you the same total amount of points as these 3 varying points per test. Your average rate of scoring is equal to the change in points that you experienced, change in accumulated total points over these 3 tests, divided by the change in tests you had accumulated. So that's 255 total change in points. You went from 0 accumulated points to 255 of them as you accumulated the experience of 3 tests. So your average scoring rate is 85 points per test. That is what a test average is. All right. If you recall from last time, speed is the absolute value of velocity. When we talk about velocity and acceleration as vectors, I'll use vector hats, but for our purposes now, we can just use absolute value signs. So I guess here's a question that I can ask. If this is the position as a function of time of an object, what is its average velocity? Well, the average velocity is the whole displacement divided by the whole elapsed time. And if you have an object that starts with an initial position of 0 meters, and by the way, 0, I can actually just say an initial position of 0, because 0 meters is the same as 0 miles, which is the same as 0 rhinoceroses. So if something is 0, you don't need units on it. But here, there is an initial position of 0 and a final position of minus 3 meters. So delta x is minus 3 meters, and that occurred over an elapsed time of 6 seconds. So 0.5 meters per second, that is the average. Oh no, there should be a negative sign there. I'm sorry. Negative 0.5 meters per second, that is the average velocity here. All right, what about the average speed? Well, the average speed is a little bit different. It's equal to the distance traveled divided by delta t. And if you remember, distance traveled is shoe leather distance. So during this jaunt, there was an accumulated distance traveled of 6 meters. Here the object is at rest, so no distance traveled. But here, going back to the origin of position, there's an additional 6 meters of distance traveled, so a total of 12 meters of distance traveled so far. Then, going down to a position of minus 3 meters, you accumulate an additional 3 meters of distance traveled. So the whole distance traveled here is 6 meters plus another 6 plus another 3 meters, and that all takes place over 6 seconds. So 15 sixths is 2.5 meters per second. One final thought to close on. What is the acceleration of an object if this is its velocity as a function of time? Well, I've asked you a bad question again, of course. Here, the acceleration is the derivative of position, and that is changing. It's slightly positive at this time instant, and more positive at that time instant. So you can't answer the question of what is the acceleration, because the acceleration is different at different instants. But you can, of course, answer the average acceleration, which, as with average velocity being displacement over elapsed time, the average acceleration is the change in velocity over the elapsed time.